Okay, so let's start. So yeah, formally I welcome you all to this course, High Frequency Analog Circuit Design. So this is lecture 1, and as you might be knowing, this is the second level analog circuits course here. And if you are wondering what you'll be learning in this course, the online response from my end is this. You'll be learning to design this triangular block. And what is this? Yeah, as you guys know, this is an operational amplifier or an opamp, right? And so say the voltages here are V1 and V2. What is the output voltage? Some gain times V1 minus V2. And ideally, what do you want this gain to be? You want this to be infinite. And what can you say about the input impedance or the input resistance looking in? That also you want it to be as large as possible. And what about the resistance looking into the output side? That you want it to be 0. Okay, great. So by the way, in what kind of applications do you think we use op-amps? Sorry?
Suppressing the noise.
Why do you say suppressing noise? Okay.
It's a differential, so that noise will be common both of them, so it will get suppressed.
I mean, that is assuming if both of them have the same noise, but as you'll be seeing, that's not what will happen usually. So, I mean, in a very generic case, sorry? Comparator. Well, okay, comparator, usually op-amps are not used as comparator, we use some other blocks usually. But yeah, you can use op-amp as comparator, but that's not its main purpose, right? My question is, you seem to have an infinite gain times some input voltage, right? So what I'm saying is, if I directly give some voltage here, the gain is infinity. So what will happen to the output? Yeah, ideally it will be infinite, but in practice it gets saturated to the supplies and grounds, right? So what's the point of this infinite gain?
You can produce oscillators for oscillators.
Not really. No, I mean, don't even go to oscillators, right? Some basic circuits that you might have seen. What are the circuits you have seen with op-amps? Sorry? Multi? Okay, so have you guys heard of negative feedback? So, I'm sure you might have seen this in one form or the other. Right, so if I call this as the input, what is the output? This is A by 1 plus A beta times V in. So I can also basically write it as 1 by beta times. So now here, if A tends to infinity, what can you say about the output voltage? 1 by beta times V in, right? So basically, if you think about it, in practice you might want to have a reasonable gain of 1 by beta, say probably 10 or 100. But the issue is you can't have a precise gain of say 10 or 100 designed as such, right? So what you do, you have a 1 by beta, which is probably 0.1 for a gain of 10, and attenuation of 0.1 you can easily get using a resistive divider like this, right? And then you put this whole thing in negative feedback, then you can get a precise gain. Okay, so op-amps, the main function is to be used in these kind of negative feedback loops, right? And the portion I have encircled is basically the op-amp, right? It takes the difference between two voltages and amplifies it by an infinite gain, right? And that's where you use infinite gain, right? Else it's kind of not really useful. Okay, and these negative feedback loops are quite, I mean, they are very important, and you'll find them in a lot of places, and even in real life, you might have encountered, right? For example, if you actually think deeply, the way you speak, right, that also has an inherent negative feedback, right? For example, if you want to speak to someone, the amplitude or the loudness level with which you speak, right, that brain has some predetermined level saying that, okay, you speak at this level so that the opposite party can hear. But how it's done, if you think about, say this is your speaker, inbuilt speaker, you will speak. Whatever you speak is basically heard back by your ears, right? So this is heard back by your ear, and it's then sent to the brain. And then the brain compares whether what you have spoken, this should be the level at which you have to speak, and then instructs the rest of your sensory organs to say, increase the level or decrease the level, right? And you might have noticed, right, if you actually wear some headphones, you tend to speak much louder than how you normally speak. That's, I'm sure everyone must have experienced. Why that happens? Well, if you have headphones, your ear is not exactly sensing what you speak. There is basically an attenuation factor beta here, right? And we just saw, if you have a closed loop system like this, what will be the output here? If, say, this is some Vin, if I have an infinite gain here, it will be 1 by beta times the input, right? So because you have this attenuation, you tend to speak much louder. That's all. Okay. So the point I'm getting is, these negative feedback systems are actually very powerful and strong, right? And op-amps are basically the crucial building blocks required in making such negative feedback loops. Okay. And now, if you think about where do I see these op-amps or negative feedback loops in real life, my answer will be to just look at your smartphones. So actually, don't look at your smartphones, look at this screen here. Okay, so this picture I've taken from Tech Insights. So this is Samsung Galaxy S20, released a couple of years back. So now if you flip the phone and take it out, which I don't recommend you to do, you'll find a lot of ICs. And this portion here you see, I don't know if it's legible here, this is basically the 5G modem. And that's basically the core of your mobile, right? Because that's what lets you make calls, browse data, browse internet through mobile data and stuff. And you'll have a lot of other stuff, but this is basically the core, okay? And if you actually look at how a wireless receiver looks like, it will look like this, or at least one half of the wireless receiver will look like this, okay? So here you'll have some circuitry. And then the second half will look like this, where you basically have an amplifier, which will be realized using an op-amp with negative feedback. A bunch of filters, again realized as op-amp, with resistors and capacitors put in negative feedback. And then we have an ADC, or the analog to digital converter. And you'll be surprised to know a lot of ADCs actually use negative feedback and op-amps. Okay, and in your phone, obviously, you have several receivers like this, right? Even your 5G phone must support 4G, 3G, etc. And it has to support for multiple bands. So you'll have several such receivers. Okay. So next time, whenever you make a call, remember that the data is actually being processed by lots of such op-amps and negative feedbacks, and that's what makes you make these calls. Okay. And in addition to these receivers, you'll also have more receivers, one for Wi-Fi, Bluetooth, GPS, NFC, blah blah blah, right? All of them basically have this kind of structure, at least second half of the receiver. Okay, and not just that, this is, you can see your phone will have a lot of sensors, right? This is one example. You have a gyroscope sensor, and here you have a pressure sensor. And again, your phone has several more sensors, right? It basically has sensors for literally everything, right? And even if you look at how the data from a sensor is processed, this is a typical signal flow. So here you'll have the sensor. The sensor will send some physical quantity, generate an output voltage here, and the voltage is basically processed in an exactly similar fashion. Okay, so not just when you make a call, whenever you touch a phone to make a call, even then, the information is being processed by several op-amps and negative feedback loops. Okay, so bottom line is, let's all be grateful for op-amps, right? And it only makes sense that I have a course dedicated for op-amps. Okay, and it's obviously beneficial to learn how to design these. And as I mentioned, you use op-amps in negative feedback loops. And when I say negative feedback, what is one issue that comes to your mind? What is one problem that can happen when you have a negative feedback loop? Sorry? Okay, I mean more. Huh? Yeah, infinite gain is not possible. You have, let's say, a large gain. But whenever you have feedback loops like this, what can potentially go wrong? What? It can become unstable. I'm sure everyone is aware of it, right? So in this course, we'll obviously look at designing op-amps, basically for negative feedback loops. So which means we need to understand how what stability is and how do you design op-amps so that when it's used in negative feedback loops, the loop remains stable. Okay. Non-linearity is a different aspect. Sometimes, see, if there is some non-linearity, the system might still be usable. But if it's unstable, it's literally not usable, right? So yeah, so we'll learn to design op-amps, learn about stability, and learn a lot about their non-idealities, like how noise is generated or how to analyze noise in analog circuits, mismatches, offset, and etc. Okay, great. So a quick info about the grading scheme. So you'll have a midsem and an endsem as usual. So midsem will account for 25% and endsem 30%. So together this will be contributing to 55% of the total weightage. You'll also have design projects and mini quizzes. So we'll have about 4 or 5 of these mini quizzes, and I'll choose basically best n-1 out of n. Okay, and this will be basically some 10-minute quizzes. Okay? And projects as of now it's 20% and this will be 25%. And the final weightage among these two can change, so this can go to 25%, this can come to 20%. This final decision I'll make it later. But together they will be contributing to 45% of the grade, and their grading, the percentage can vary from 20 to 25. Is that okay? Cool. So with all the logistical information carried out to you, let's start with the course today. So what I'll do is in the first 1.5-2 classes, I'll refresh the basics that you'd have learnt in previous circuits course, so that everyone is on the same page. So of course our main aim is to design this guy, an op-amp. Remove this. And as you guys told, the output voltage here is a large gain times the input it sees. So what kind of a controlled source this is? So it provides an output voltage. So it's a voltage source basically, and the voltage is in response to some voltage it senses. So it's basically a voltage controlled voltage source, right? So if I were to model it, this is how it's going to look like. So this is V1, V2, and you'll have okay. But on ICs it turns out it's much easier to implement a voltage controlled current source. Okay, so instead of realizing an op-amp, what we'll do is we'll usually implement an operational transconductance amplifier or OTA in short. Okay. So this is basically a voltage controlled current source, which means if I apply a differential input V1 minus V2, what is exactly controlled is the current coming out of this block, right? And this current will be some GM times V1 minus V2. Okay. And of course, this current will flow through the output resistance this block has, and that will give our output voltage to be GM R out times V1 minus V2. Okay. So basically you still realize the output voltage to be a large gain times the input difference voltage. So what is the difference between these two guys? So basically here the output resistance is basically 0 ideally, right? Whereas here you see that the output resistance determines the gain, right? So ideally what should, how do you want this output impedance to be here? I mean, question is simple, right? This is the gain I have, GM times R out. So how should R out be so that I have a large gain? It should ideally be infinite, right? So here the output impedance will be infinity, right? Because this basically is a current source. Okay. So that's the only difference. And the reason realizing a voltage controlled current source is easy is because the active devices we have are all MOSFETs, and I'm sure these guys must be familiar to you. The terminals are gate, drain and source, and we try to bias this bias the transistors usually in saturation region, because that's where you get the maximum intrinsic gain. And in saturation region the drain current is half UNCOX W by L VGS minus VTH whole square, and if you have channel length modulation you will have this guy also. Okay. Now although this relation is quite non-linear, if you are only interested in how the current changes in response to small changes in the terminal voltages, how does it behave for small changes? If I change the gate to source voltage by a small delta V, what is the change in the current? I mean, basically this is a nonlinear function, right? So what I'm saying is, let's say this is at some fixed VGS. Around it I am varying it by a small delta V. You can approximate as a linear relation, and that's what gives a small signal model, right? And hopefully you guys are familiar with this small signal model, right? This is the gate, drain and source. So we'll have a incremental drain current, which is GM times the incremental gate to source voltage. We'll also have output impedance R0 or RDS, and this is basically 1 by lambda times the current flowing. Okay. Now not just a MOSFET, if you take any kind of devices, right, starting from vacuum tubes, bipolar transistors, MOSFETs, FinFET, or any devices we'll have in the future, they will all be some kind of a voltage controlled current source like this. Okay. So that's why it makes sense that it's much easier to implement a voltage controlled current source on ICs. Okay. Now just like you have an NMOS, you also have the PMOS counterpart. So this is the gate, source and drain. So here you had a current flowing from drain to source in response to a non-zero gate to source voltage and drain to source voltage. In PMOS, where does the current flow? From which terminal to which terminal? Source to drain. And this will be in response to a non-zero source to gate voltage and source to drain voltage. That's the only difference. So again, if I were to draw the incremental linear model, this will be gate, drain and source. You will have an incremental current flowing from source to drain, and then you have the same or not here, and the magnitude of the current is Gm times VSG, right? And I can modify it as Gm minus Gm times VGS. So now I can take this sign out here and then say the current is flowing in the opposite direction. Okay. So the point is, with respect to the small signal linear behavior, there is virtually no difference between having an NMOS transistor or a PMOS transistor. Okay, great. So now that you guys know MOSFETs produce or respond to voltages applied to between gate and source, you know that we have an output between drain and source, that is current flows from drain to source in response to input voltage applied between gate and source. So this basically gives us few combinations to play around, right? So I can apply the input at the gate, see the output at the drain, apply input at the gate, see the output at the source, and this is the last combination. So let's quickly go through all these three. So first combination is where I'll take the MOSFET, I'll apply an input at the gate and observe what happens at the drain, right? So I'll make sure the source is grounded, and here let us say have a resistor connected like this. Yeah, and of course always remember that you always have a bias voltage here so that the MOSFET operates in saturation region, right? That I'll not show explicitly. So if I apply a small signal voltage V in here, what can you say about the small signal output voltage? What is that? Gm times RD parallel R naught times V in. Okay, it's straightforward, right? Because in small signal you'll have a current Gm VGS. So Gm VGS is basically V in, and then you have R naught like this. So you have a current minus Gm V in flowing upwards, and that flows through a resistance R naught and RB, right? Great. So this is called the common source configuration. So next let's look at the second possibility, where I'll apply the input at the gate and observe the output at source. So in this case I'll connect the drain to VDD so that it's in saturation. Again, there is some bias voltage here which I am not showing explicitly, and say you have a current source here. Okay. So can you tell me what will happen to the output voltage if there is an increment in V in? V out is what? V out is? No, it is V in. Why? Input impedance is? This one. Okay, so? Okay, see here you don't even have to go to small signal, right? See, Here, what is the current flowing through the transistor? I0. That is fixed by this current source. Irrespective of what input you apply to the gate, the current is fixed to be I0. For a fixed current I0, you need a particular gate to source voltage. Okay. So here let's assume R0 is infinity. Okay. So the current is basically determined only by the gate to source voltage. Right. So to have a fixed current I0, the gate to source voltage must be a fixed quantity. So if the gate voltage increases by V in, source voltage must also increase by the same factor, so that we have a fixed gate to source voltage, right? So this basically, the incremental Vout is same as increment in V in, that's all. Okay. So now you see that I have basically a gain of 1, right? So what's the point of this?
Buffer.
So what's a buffer?
Output resistance.
Yeah, so basically, let's say I have an input source like this, right? It might have its own series resistance. So let's say I want to transfer this input voltage to a load resistor RL, right? If I directly make this connection like this, what is the output voltage? Yeah, so let me make some space here. So this is going to be RL by RL plus RS, right? So if RL is small, basically you see that the voltage is not getting transferred completely. So that's why you put a buffer. So the buffer is going to offer a high input resistance, ideally infinity, so that this voltage source transfers its information completely here, and the buffer basically copies this voltage to the load resistor, ideally with a zero output resistance, but in practice you might still have a small output resistance. Okay. So here, what is the input resistance for this guy? Infinite, because we are looking into the gate. So this is fine. What about the output resistance? Okay, so let's quickly do that, right? So this is the configuration we have. Okay, again let's assume R0 to be infinity to start with. Here I apply the input. So to find the output resistance, what should I do? Basically I need to find how at this node, if I apply a test voltage, a small signal test voltage, what is the small signal current that is drawn, right? And in small signal, what will happen to the current source? It's an open circuit. Yeah, so let's do that quickly. So of course I'll make sure the input is also de-energized, so it's ground. So if I quickly draw the small signal, you see that you have Gm times VGS here, where gate is grounded, and at the source I have applied a test voltage Vt. So this current is what? What is the current flowing in this direction? Minus Gm times Vd, right? So which means the current flowing up, this is Gm Vt, right? So it looks like at this node, if I apply voltage, a current Gm times Vt is pulled out of that node. So this basically corresponds to a resistor with a value of 1 by Gm. Okay. So the output resistance here is 1 over Gm. Okay, so now what will happen if we have R0? It will just come in parallel, right? Because if you have R0, the output resistance, the RDS or R0 of the transistor will be between the source and drain. Drain is grounded, so I can say it appears like this. So the output resistance will be 1 by Gm parallel R0, and for all practical purposes it's approximately 1 by Gm, right? Because Gm R0 is much greater than 1. Okay, so 1 by Gm will be much smaller compared to R0, so the lowest resistor will dominate. Okay, So here you see that we have an infinite input resistance, but the output resistance is what? 1 over Gm. So this is not an ideal voltage buffer, but it's a decent voltage buffer. Okay, so not an ideal buffer. And what configuration is this called? This is common drain, right? Because the drain terminal is basically not doing anything here, right? Okay. Now, yeah. So now, please remember that the the impedance looking into the source is not always 1 by Gm. Okay. So it basically depends on the resistor you have at the drain. Okay. So this simply because, let's say you have instead of RD, let's say you have a current source. Okay. So what is the incremental impedance of a current source? Infinite. That basically I'm saying that we have an infinite RD. Okay. So now if I try to find the impedance looking into the source, so again I'll apply an incremental test voltage here. So this is an open circuit here. So what will be the current flowing like this? 0. So what is the impedance? Infinite. Okay. So in this case it's infinite, right? So the impedance looking into the source is not always 1 by Gm. It actually depends on the resistance you have at the drain. So please take it as an exercise and work out what R out is in this case. Include R naught also. Okay. It doesn't come like that actually. Work it out. What did you say? No, it doesn't come like that. Work out, right? Because see, RD comes here.
R naught plus RD from 1 plus mu and d by RD.
Yeah, I mean, work out and check it, right? So what you will find out is this will be valid. Okay, I mean, from what you have seen now tell me, this output resistor will be 1 by Gm for small values of RD or large values of RD? Small values of RD, right? I mean, now small is like a vague quantity, right? So with respect to what should I compare RD with? What is the other resistor you see here? Sorry? No, what I'm saying is, everyone agrees that for small values of RD, the resistance looking into the source is 1 by Gm. But what I'm saying is, small is a vague term, right? I should basically, if you say small, which means I'm comparing RD with something else. So yeah, so if you'll find that if RD is much smaller than R naught, then the impedance looking into the source is approximately 1 by G, right? And the limiting cases, if you have infinite R naught, then you don't even have to worry. Okay, great. So yeah, so now let's say instead of the current source here, I have a resistor here. Again the same thing. So what will happen to the incremental output voltage? Sorry? Yeah, what did you say? Yeah, so you can again work it out. Again here assume that R naught is infinity. So you'll find that it's GMRS by 1 plus GMRS times Vin. Okay. So I mean, let's quickly see if this makes sense, right? I mean, whenever you derive an expression, you do some sanity checks, right? So what is one quick sanity check I can do? Yeah, I can tend Rs to infinity. That corresponds to the current source I had in the last case. If I tend Rs to infinity, what happens to the V out? It tends to, it becomes equal to Vin. That's exactly what we had earlier. Now you also notice if I make Gm to infinity, What happens to V out? Huh? V in. Why does that make sense? Sorry? Yeah, I mean it's an ideal buffer, but why if I make GM to infinity it's an ideal buffer? So I mean, one way to look at this, we saw the impedance looking here is 1 over GM. If GM is infinity, the output resistance is 0, so it's an ideal buffer. That's one way to look at it. See, the other way is if I have it like this is V in and V out, right? I know that the output voltage is some finite voltage, right? So which means I am going to have a non-zero drain current flowing in the transistor. And what is the drain current with respect to the gate to source voltage? Yeah, I mean small signal, right? Everything is in small signal. It's GM times VGS. Okay. Now what I'm saying is GM is infinity. Right? If GM tends to infinity, to have a non-zero drain current, what should happen? VGS must go to 0, right? So VGS will go to 0, right? So which means V out will be equal to V in. Okay. So this is something like the virtual ground you have, right? So in op-amps you have the virtual short, right? If you have a feedback here, you know that if I call it some Vx, V in will be Vx, right? Why is that so? Because we have an infinite gain, so the output will be an infinite gain times V in minus Vx. So to have a finite output, this difference must go to 0. Okay, great. So enough about common drain. Let's look at the last combination. So here I'll apply the input at the source, take the output at the drain. So I'll short this guy, and this is the incremental picture. I'm not showing the DC biases. Okay, so I'm applying voltage V in at the source, and say I have a resistor RD like this. And again, let's first assume R0 is infinity. So this is the output voltage. What is the output voltage? GMRD, right? Because now you just have GM VGS current like this, right? VGS is basically minus V in, which means I have a current GM V in flowing in the in this direction. So this current flows to a resistor RD. So that gives the output voltage as GM RD times V. Okay. Now the more common use of this circuit is to use it like this, where instead of applying a voltage at the source, you have a current as the input. Okay, it's a small signal current. And here you see what is the small signal current at the drain term. So what can you say about the small signal current I out in terms of the input small signal current I in? It's same, right? Again, I'm assuming R0 is infinity. So whatever current flows here has to come, right? I mean, the direction I think I kind of messed it up. So in this direction it's same. So here you see that the output current is equal to the input current. So what's the point of the circuit? It's a current buffer, right? So just like with the voltage source, we have an input current I in, it will have its own parallel resistor, right? So now if you want to transfer this current completely to a load resistor RL, this is a trivial way to do it, right? But by the way, when will a current source be happy to deliver all the current to RL? For larger values of RL or smaller values of RL? For small values of RL, this current IN will completely flow, right? So it's okay if you have a small RL, but if you were to transfer this current to a large load resistor, this definitely is not going to work. And that is why you put a current buffer, which basically provides a zero input resistance, so that the current source completely transfers its current, and then this guy will make a copy of this current and transfer it like this. Okay, so this is basically a current controlled current source. And similarly, this guy, where did it go? The voltage buffer is what kind of a control source? Voltage control? Voltage source. Voltage buffer is basically a VCVS. A current buffer is basically a CCCS. Okay, great. So this is all nice, but our goal is to make an op-amp with a large gain, right? And of course, we know that common source is a good candidate because common source we saw provides a large gain, right? Common drain was basically a VCVS, and common gate was a CCCS, right? So we can start with the common source configuration. I'll apply say V1 here, and I connect RD, but this just amplifies the voltage V1. But in an op-amp, what do we want? What should we amplify? Difference between two voltages. So obviously one trivial way is to apply the second voltage here, because then the incremental current is Gm times V1 minus V2, and that flows through RD to generate the required voltage. But what's the issue with this? Yeah, so here for the ideal op-amp, looking in both V1 and V2, what is the impedance? Infinite. But here looking into V1 it's infinite, but when you look into V2, what's impedance? 1 by Gm, right? It could be very small. So now we have an issue where you are trying to deliver this voltage V2 to a small impedance. So what can I do? Yeah, I mean, this is exactly what we saw here, right? Where is it? Yeah. So here, this is the same thing, right? We wanted to transfer this voltage to a small load. We saw that we can't connect it directly. So instead, we decided to put a voltage buffer. So we'll do the exact same thing now. So I'll take this guy, no change here. So instead of connecting V2 directly, I'll do this. This should work, right? So now the impedance looking here is infinity, looking here is infinity. The incremental current is Gm times V1 minus V2, and that flows to the output and generates the required voltage. Okay, this is good, but how can I implement this guy? What is the circuit that can realize this? It's that common drain configuration, right? So what I'll do, I'll replace this guy. So first let me draw V1. Fine. So instead of this buffer here, I'll replace this buffer with source follower or common drain. So I'll apply the voltage at the gate, take the output at the source and connect it. Okay. So and then I'll just do this. Fine. And here I'll have to take the output. Okay. Now of course the other change you can do is you can also have a resistor here to make the structure symmetric, right? which means you can now take the output either here or here in one of the arms, and this basically gives rise to the differential amplifier you guys are familiar with. So I'll redraw the circuit here. So here I have V1, here I have V2, V0, RD and RD, and let's say I take the output here, it doesn't matter. Okay, great. So let's try to calculate what is this output voltage. Okay. Now one thing we know for sure is that if you use an ideal buffer here, oops, what is this guy? If you use an ideal buffer here, then the incremental current is Gm times V1 minus V2, and what will be the output in that case? Say R0 is infinity. Basically the incremental current Gm times V1 minus V2 that flows into the resistor here. The current, do it properly. So the current flowing in this direction is Gm V1 minus V2. So which means the current flowing up is what? Minus Gm times V1 minus V2. This current is basically flowing through this resistor RD. So ideally the gain is minus Gm RD if you have an ideal voltage buffer, but we know for a fact that this guy is not an ideal buffer, right? Why is it not an ideal buffer? What is the non-ideality in this? Output resistance is not 0. What is the output resistance for this guy? Common whatever. What is this? 1 by Gm. So this is obviously not an ideal buffer. So let's try to see what happens to the gain. Okay. So of course now we know what is the incremental gate V1. Incremental gate voltage here is V2. So let's try to find out what is the incremental source voltage, right? And you can do it in multiple ways. One quick way is to draw the small signal equivalent. Again, let's start with assuming R0 to be infinity. So let's quickly draw it, right? So for the transistor here, let me label these guys. So let's say this is M1 and M2. For M1, I'll have a Gm VGS in this direction. Gate is at V1. For M2, I'll have a Gm VGS. Gate is at V2. Both their sources are shorted. And what should I connect here? Open circuit. So what is this current? Gm times V1 minus Vx. Okay. So basically gate voltage minus source voltage. Similarly here, what is it? Gate to source voltage of second transistor, which is V2 minus Vx. Right. I'll have of course RD here, which let's keep it for now. So and this voltage is Vx, right? So if I apply KCL at this node, some of the currents entering is 0, so that's basically Gm times V1 minus Vx. V2 minus Vx is 0. So what do I get for Vx? It's basically the average of the two. Okay. So now I know that this voltage is V1 plus V2 by 2. So what is the small signal current I1 here and small signal current I2 here? What is I1? Huh? No, why it's Gm by 2? No, small signal current through M1 is Gm times the gate to source voltage. That's all, right? So Gm times gate voltage is this, source voltage is this. So what is this? Yeah, Gm times V1 minus V2 by 2. Fine. Similarly, I2 is what? Gm times. So this basically minus Gm times V1 minus V2 by 2. So if I call this guy as output voltage, what is my output in terms of the current I2? Huh? No, in terms of the current I2, what is the output voltage? It's minus I2 times RD. Is that okay?
Yes.
So what is the gain then? I have Gm RD by 2. Okay. So now you see that the gain has dropped down by a factor of 2 compared to having an ideal buffer. Okay. And that's simply happening because common drain or the source follower is not an ideal voltage buffer, and that's why we have it. Okay. So just one more thing, let me cover it. So let me also tell you quickly how you can find the source voltage, probably by inspection. See, right? So this is the configuration we have. So now of course Vx has contribution both from V1 and V2, right? So first let's quickly find what is the contribution from V1, V2. So if you think about it, all you have is V2 here, and at the source I see that I have some resistor connected. What is the equivalent resistance looking in this direction? 1 by Gm. Okay. So it's as if I have done like this, right? And this is what is Vx. So what configuration is this now? I'm applying an input at the gate, taking the output at the source. It's like a source follower. So what will be Vx in terms of V2? If we had a resistor Rs here, this would have been something like this. Okay. So instead of Rs I have 1 by Gm. So what does it simplify to? It becomes 1 by 2, right? So due to V2 we have a contribution of V2 by 2. Similarly, due to V1, what do you think the contribution will be? Same, it's basically the symmetric circuit, so that's why you have this. Okay, great. So just one last thing. So here you have a current source here, right? And in practice you will see that on IC implementations, transistors are biased with a constant current like this, simply because it's easy to copy and replicate currents than replicating voltages. Okay, how can I replicate currents? Huh? So I'm sure you might be aware of current mirrors like this, right? So if this is a current I0, I can basically copy it to multiple transistors, or even get a scaled version of it, right? Great. And what is the resistance looking here? It's just the R0 of the transistor. Now if you want to improve it, one thing you can do is, I have a current source, I want to make it a better current source, I can put a current buffer here, right? This is a current buffer. Okay, that will basically make it a better current source. And what is the current buffer, Common gate, right? I will apply the input current at the source, take the output at the drain. So this should act like a better current source. And what do you know what this guy is called? Have you guys called cascode? Okay, and please take it as an exercise and find out what will be the output impedance of this. Okay, so we'll continue from that in next class. So this, let's say the transistors are M1 and M2. Consider R0 obviously. So find out what will be the output resistance, right? And we'll pick up from this point. Okay. Yeah. Thanks. Sorry. Yeah. I hopefully let's see.